Imagine a tiny realm where particles exist in multiple states at once, defying our everyday intuition. Welcome to quantum mechanics, where the universe is woven from uncertainty and paradox. This realization marked the birth of a revolutionary theory that forever changed our understanding of the universe.
This realization sent shockwaves through the scientific community. Quantum mechanics underpins many technologies we rely on today, from lasers to transistors. Despite its success, quantum mechanics remains deeply mysterious, attracting some of the greatest minds in history.
Their debates and discoveries have shaped our understanding of the quantum world. We will explore key concepts like superposition and entanglement, and meet pioneers like Niels Bohr and Richard Feynman. Quantum mechanics forces us to confront fundamental questions about reality and the limits of knowledge.
To grasp quantum mechanics, we must shrink to the subatomic realm. Here, particles like electrons and photons behave in ways that defy classical physics. This inherent uncertainty is the driving force behind many of the quantum world's most intriguing phenomena.
Superposition allows a quantum particle to exist in multiple states at once. Schrödinger's cat illustrates this concept. The cat is both dead and alive until observed. This ability to occupy multiple states has profound implications.
Entanglement links particles in a way that transcends space. Measuring one entangled particle instantly reveals the state of the other, no matter the distance. Entanglement is foundational for emerging technologies like quantum computing and cryptography.
The double-slit experiment reveals the wave-particle duality of light. Photons create an interference pattern, behaving as both particles and waves. Each photon seems to explore all possible paths, highlighting quantum weirdness.
Schrödinger's cat highlights the observer effect in quantum mechanics. The act of observation forces a quantum system to choose a definite state. This raises profound questions about the nature of reality and the role of the observer.
Quantum tunneling allows particles to pass through barriers. This phenomenon is essential for the workings of the sun and electronic devices. Quantum mechanics reveals a reality far stranger than we could have imagined.
Einstein, despite his brilliance, had reservations about quantum mechanics. He believed it must be an incomplete description of reality. His debates with Niels Bohr shaped the development of quantum mechanics.
Niels Bohr's Copenhagen interpretation embraced quantum uncertainty. Bohr argued that observation forces a quantum system into a definite state. Instead of forcing quantum mechanics into classical physics, we should explore its profound implications.
Section 3. Feynman's Sum Over Histories. Dancing with Possibilities. While Einstein and Bohr debated the philosophical foundations of quantum mechanics, a young American physicist named Richard Feynman was busy developing a new way of thinking about the quantum world. Feynman, with his unique blend of creativity and scientific rigor, sought to unravel the mysteries of the quantum realm in a manner that was both innovative and deeply insightful. Feynman, known for his playful demeanor and unconventional approach to physics, introduced the path integral formulation, also known as the sum over histories approach. This groundbreaking method revolutionized the way physicists understood quantum mechanics, providing a new lens through which to view the behavior of particles at the smallest scales. Feynman's approach was based on the radical idea that a quantum particle, in its journey from point A to point B, doesn't simply follow a single path, but explores all possible paths simultaneously. This concept, was not only revolutionary, but also challenged the traditional notions of determinism and predictability in physics. Imagine a particle taking a leisurely stroll through a park. In this quantum park, the particle doesn't just choose one path, but rather explores every conceivable route, no matter how winding or improbable. In the classical world, it would follow a well-defined path from start to finish. This path would be predictable and straightforward, much like a person walking along a clearly marked trail. In Feynman's quantum park, however, the particle would explore every possible route, zigzagging, looping back on itself, even venturing into the forbidden territory of nearby trees. This whimsical journey through the park illustrates the core of Feynman's idea that every possible path, no matter how strange or unlikely, plays a role in the particle's journey. Each path, no matter how improbable, contributes to the final probability of finding the particle at point B. This means that even the most bizarre and unexpected routes have a say in the particle's ultimate destination. Feynman's approach, while mathematically equivalent to other formulations of quantum mechanics, offered a fresh and intuitive way of visualizing the quantum world. It allowed physicists to think about quantum phenomena in a more accessible and imaginative manner. It emphasized the inherent fuzziness of quantum reality, where particles dance through a superposition of possibilities, their ultimate fate determined by a cosmic game of chance. This dance of possibilities is a beautiful and poetic representation of the quantum world, where certainty is replaced by a tapestry of potential outcomes, each woven into the fabric of reality by the probabilistic nature of quantum mechanics.
The EPR paradox, a challenge to locality. Even as quantum mechanics succeeded, a nagging unease lingered, particularly for Albert Einstein. Entanglement implied a spooky, faster-than-light connection between particles. This troubled Einstein, who believed it violated the fundamental tenet of locality. In 1935, Einstein, Podolsky, and Rosen devised the EPR paradox to challenge this. Measuring one particle's spin instantly determines the other's, regardless of distance.
Section 2. Bell's theorem, the fall of local realism. For Einstein, the idea that one particle could instantly influence another, even across vast distances, was preposterous. It violated special relativity, which stated nothing could travel faster than light. He believed correlations in entanglement could be explained by hidden variables. This debate raged for decades. The resolution came from an experimental test. In 1964, John Bell proposed a theorem to test quantum mechanics against local realism. Bell's theorem provided a way to test the heart of quantum mechanics. If quantum mechanics was correct, results would violate Bell's inequalities.
Section 3. Quantum Reality, a tapestry of possibilities. The stage was set for a showdown between two of the most fundamental principles in physics, locality and realism, versus the bizarre predictions of quantum mechanics. This clash was not just a theoretical debate, but a profound exploration into the very fabric of reality itself. In the 1980s, physicist Alain Aspect, along with his team, conducted a series of groundbreaking experiments using entangled photons that delivered a decisive blow to local realism. These experiments were meticulously designed to test the limits of our understanding of the quantum world. Aspect's experiments and numerous subsequent experiments consistently violated Bell's inequalities, confirming the predictions of quantum mechanics and demonstrating that the universe is fundamentally non-local. The implications were profound, shaking the very foundations of classical physics and opening new doors to understanding the universe. The world, it seemed, was far stranger than even Einstein had imagined. The peculiarities of the quantum realm defied common sense and challenged our deepest intuitions about how the universe operates. The fall of local realism forced physicists to confront the possibility that reality is not a collection of independent objects, each with its own well-defined properties, but rather a web of interconnected potentialities a tapestry woven from the threads of entanglement. This new perspective required a radical shift in how we perceive the nature of existence. This interconnectedness, stretching across vast distances, challenged our very notion of space and time. It suggested that the separation we perceive in the macroscopic world might be an illusion, a mere artifact of our limited perspective. If particles could communicate instantaneously, even across the universe, did distance have the same meaning in the quantum realm? This question opened up a Pandora's box of possibilities, hinting at a reality where the conventional boundaries of space and time are blurred. The implications of non-locality extended far beyond the realm of theoretical physics. It suggested that the interconnectedness observed at the quantum level might have parallels in other domains, potentially influencing fields as diverse as biology, consciousness studies, and even social sciences. It hinted at the possibility of a deeper interconnectedness in the universe, a cosmic web of relationships that transcended our classical intuitions. This profound interconnectedness could be the key to unlocking new understandings of the universe and our place within it, weaving a tapestry of possibilities that stretches beyond the limits of our imagination.
Section 4. The quest continues. Exploring the quantum frontier. The resolution of the EPR paradox and the experimental confirmation of Bell's theorem marked a turning point in our understanding of the quantum world. It demonstrated that the universe is fundamentally non-local, a place where entanglement reigns supreme and the seemingly impossible becomes possible. Yet, even as these discoveries solidified the foundations of quantum mechanics, they also opened up a Pandora's box of new questions and mysteries. What is the true nature of this interconnectedness? Can we harness the power of entanglement for technological advancements? Does the non-local nature of reality offer any clues about the ultimate fate of the universe or the nature of consciousness? The quest to unravel the secrets of the quantum continues, driven by a profound curiosity about the fundamental nature of reality and the desire to push the boundaries of human knowledge. As we delve deeper into the quantum realm, we can be sure to encounter even more surprises, more mind-bending paradoxes, and more awe-inspiring revelations about the universe we inhabit.
The profound strangeness of the quantum world, once confined to the realm of theoretical physics, is now spilling over into the world of practical applications. This shift is not just a leap in technology, but a paradigm shift in how we understand and interact with the universe at its most fundamental level. The same quantum principles that baffled Einstein and Bohr are now being harnessed to develop revolutionary technologies that promise to reshape our future. These principles, once the subject of intense academic debate, are now the foundation of cutting-edge innovations. Imagine a computer so powerful that it could solve problems in minutes that would take classical computers billions of years. This isn't science fiction, it's the potential reality of quantum computing. Such a machine could crack the codes that protect our financial transactions, or simulate the intricate workings of complex molecules to design life-saving drugs, opening new frontiers in medicine and cybersecurity. This is the promise of quantum computing, a field on the cusp of revolutionizing computation as we know it. The implications are vast, affecting everything from artificial intelligence to climate modeling, potentially solving some of the most pressing challenges of our time. Instead of bits, which can be either 0 or 1, quantum computers employ qubits, which can exist in a superposition of both states simultaneously, thanks to the magic of superposition. This fundamental difference allows quantum computers to process information in ways that classical computers simply cannot. This allows quantum computers to explore a vast number of possibilities simultaneously, giving them an exponential speed advantage for certain types of calculations. The potential applications are staggering, from optimizing complex logistical operations to advancing machine learning algorithms. But quantum technology extends far beyond just computation. Its reach is broad, touching various aspects of technology and science. Quantum cryptography leverages the principles of entanglement to create unbreakable encryption keys, ensuring secure communication in a world increasingly reliant on digital information exchange. This could be a game changer for industries that depend on secure data transmission, from banking to national security. Quantum sensors, with their exquisite sensitivity, could revolutionize fields ranging from medical imaging to materials science, allowing us to probe the world with unprecedented precision. These sensors could lead to breakthroughs in early disease detection, environmental monitoring, and even the development of new materials with unique properties.
The technological implications of quantum mechanics are undeniably exciting, but perhaps even more profound are the philosophical questions it raises about our place in the grand scheme of things. For centuries, we've viewed ourselves as separate from the universe, objective observers peering in from the outside. Quantum mechanics, however, challenges this anthropocentric view, suggesting a deeper connection between the observer and the observed. The observer effect, so vividly illustrated by Schrödinger's cat, raises the perplexing possibility that consciousness itself might play a role in shaping reality. Does the universe exist in a definite state before we observe it? Or do our observations somehow participate in bringing that reality into being? These are not just idle philosophical musings. They strike at the very heart of what it means to exist, to observe, to be conscious in a quantum universe. Some physicists believe that consciousness might be an intrinsic property of the universe, as fundamental as space, time, or energy. Others speculate that our understanding of consciousness itself might need a radical overhaul in light of quantum mechanics, suggesting that our minds might be entangled with the very fabric of reality.
Despite a century of groundbreaking discoveries, quantum mechanics remains an enigma, a puzzle box with many layers yet to be unraveled. We've only just begun to explore the vast, uncharted territories of this strange and wondrous realm, and many mysteries continue to tantalize physicists and philosophers alike. The interpretation of quantum mechanics, the very meaning behind the mathematical formalism, remains a subject of intense debate. Is there a single interpretation that can encompass all the bizarre aspects of the quantum world? Or are we destined to navigate a multiverse of interpretations, each offering a different glimpse into the nature of reality? The relationship between quantum mechanics and gravity, the other pillar of modern physics, remains one of the greatest unsolved mysteries in science. How do we reconcile the smooth, continuous fabric of space-time, described by general relativity, with the discrete, probabilistic nature of the quantum world?
The quest to understand quantum mechanics is not just a scientific endeavor, it's a journey into the heart of reality itself. It challenges our assumptions and expands our imaginations. As we probe the quantum realm, we encounter surprises and paradoxes. The universe is far stranger and more wondrous than we imagined. The quantum is the key to unlocking its deepest secrets. This journey requires embracing uncertainty and questioning assumptions. For those brave enough, the rewards are immense. The quantum world challenges us to expand our minds and embrace the unknown.
Our journey through the quantum realm has taken us from the heart of atoms to the edge of reality, revealing a universe far stranger and more wondrous than we could have imagined. We've encountered particles that exist in multiple states at once, defying our everyday intuition. We've witnessed the magic of entanglement, where particles separated by vast distances remain mysteriously linked. The quantum world, once considered an esoteric realm, is now emerging as the foundation for a new era of technological innovation. Quantum computers promise to revolutionize fields ranging from medicine to materials science, but in its profound impact on our understanding of the universe and our place within it. Quantum mechanics has shattered our classical illusions, revealing a reality woven from the threads of uncertainty, entanglement, and possibility. The universe is an interconnected web of relationships, a cosmic dance.